Okay, one last video number 4 in the series, which I didn't mention earlier in the live meet, but I've just decided to finish off with this, and then you'll have plenty of questions to do that you'll know all the answers for. Okay, so video number 4, and we're going to look at the wedge fringe equation, the thin air wedge. That's the equation. That's the equation on the formula sheet that you get given. Okay, so I want to have a look at and see what happens when you start messing around with these. There appears to be quite a few problem and exam questions with what happens if you change the frequency, what happens if you change the thickness of the object propping up the two microscope slides, what happens if you change the shape of the microscope slides, how does changing things here affect the fringe spacing? Okay, so what do we mean by that? So let's have a look at our thin air wedge. And there's a thin air wedge, and it's propped up with something quite thin. And here's the same thing, but this time it's propped up with something much bigger. In other words, what happens if you increase this distance here? What happens? Well, we've got an idea of what happens with what we see. We see a set of constructive and destructive interference fringes, which basically means we see some black areas and some white areas. Okay, so the formula again is this: delta x equals lambda L over 2D. So what's everything here? Delta x is how far apart are the fringes. So we know we have a dark fringe here, and we have another dark fringe here. And delta x is how far apart are these fringes. And that appears in this formula to depend on what the wavelength of the light is, how long the bits of glass are, and how far apart, that's D that way, how far apart the two bits of glass are at the end. And D here is much bigger than D here. So let's do these one at a time. So the first thing we're going to look at is what happens to the fringe spacing if this becomes bigger. Well, everything else stays the same. So lambda L divided by 2 is a constant. So delta x is proportional to some constant, is equal to some constant, which could be lambda L over D, because that's staying constant. If that stays constant, then all we've got to look at is how does that vary as D varies. And if you wanted to, you could make this equal to a constant times 1 over D, where that constant is just the wavelength staying the same, the length staying the same. It's supposed to be the same length in each diagram. Obviously 2 stays the same. So what we've got really is that the fringe separation, how far apart are the black bands, that depends on 1 over D. So if D becomes bigger, then delta x becomes smaller. So as this thickness increases, so the slit separation decreases. So what you would see in a diagram form is you'd actually see these quite far apart, these fringes quite far apart. Whereas in this one, as this gets bigger, as D gets bigger here, delta x becomes smaller. So you'd see these fringes becoming closer together. So you could be asked to draw a sketch of what the fringes look like, or you could just be asked to describe what the effect is. You could also be asked to say, well, how do you know that this becomes less? And you'd have to use the formula that's on the formula sheet, get rid of the stuff that you're not really interested in, that isn't changing, and say, right, okay, this becomes bigger, then that becomes smaller as a result. Now, in fact, there's something else which goes on here, is that, and it's not obvious from the equation at all, is that when you've got a small prop height, when you've got something that's quite thin there, these fringes are actually quite wide, and that's not at all obvious from the formula. And this is just something you're going to have to learn. And when you make this distance bigger, then the fringe separation gets less, as we've just seen, but also the actual width of the fringe itself gets thinner. So that's a second consideration that you will have to remember. Okay, as D gets bigger, and don't use arrows like this in a written example because the SQA hate this, but as D gets bigger, the fringe separation delta X gets less, and the fringes themselves get thinner. So that's a wide dark fringe caused by destructive interference, and we know we always get a dark one at the end when that thickness is nothing. Okay, we've done the maths of that. You've seen that in an earlier video. Also, the spacing gets less and the fringes themselves get thinner. That's something you're going to have to remember. Okay, thinner fringes. Okay, so that's the first thing we can look at. Now, what happens if we have a situation where I've got exactly the same setup? So I'll try and make it look exactly the same. Okay, that's supposed to be the same as that, but we change the light. You see this with monochromatic light. So what happens if we change the wavelength? What happens if we change the wavelength of the light? Okay, so D, that height, is staying the same. I'm not changing that height D. That's supposed to be the same height there. D is the same. All I'm doing is I'm shining some light on here and seeing the reflections. What happens if the wavelength gets bigger? Well, let's make the mathematical bit of this is the length stays the same, 2 stays the same, D stays the same. So we've got a constant bit here, L, 2 and D. L over 2D stays the same. So we've got that delta X is equal to some constant, L over 2D, multiplied by lambda, and K is L over 2D, as I've just said. So if you make the wavelength bigger, then you will see the fringe spaces get bigger. Now, what sort of light has a bigger wavelength? Well, for instance, red light has a wavelength which is way up in the sort of 600 nanometer range, whereas green light has a wavelength of somewhere near 500. I'm just picking these numbers out. You can actually find exact numbers on the, not the formula sheet, but on the data sheet. And when you get right down to blue light has a much smaller wavelength, a much smaller wavelength. So as you go from red to green to blue, when you're making the wavelength smaller and smaller and smaller, then the slits, the fringe spacing will become less. So you'll still see fringes quite wide, but you'll see them closer together like that. Okay, that's your second option, is what happens when the wavelength changes. We've looked at what happens when the thickness changes. We've looked at what happens. The second option now looked what happens when the wavelength changes. What happens when the frequency changes, the frequency of the light? Well, you probably know, and you can probably remember that wavelength and frequency go they're back to front, they're inverse, because we've got V equals F lambda. So lambda equals V over F. Okay, and V is a constant, 3 times 10 to the power of 8. So if F becomes bigger, if the frequency becomes bigger, the wavelength becomes smaller. So in the electromagnetic spectrum, we've got waves right down at the radio end have got long wavelengths, and they've got a low frequency. And up the other end, by the time you get up to gamma, and you've got Roiger-Biv, you've got the light bit in the middle, you've got short wavelength, and you've got a high frequency, low frequency. Up this end, you've got a high frequency. So high frequency means a big frequency, a higher frequency. So if F is a higher, bigger number, okay, if that becomes bigger, then that has a matching short wavelength. Okay, big number on the bottom, lambda's a small number. If you do it the other way around, if you have a small or low frequency, then the wavelength is much longer. So you can reword the second option of what happens to the spacing with the wavelength. You can now have a look and say, well, what happens with the frequency? Okay, so you could describe now that if you've got a high frequency beam of light shining on here, you could describe the difference between what you would see with a low frequency beam of light. So mathematically, you'd have to rewrite this, and you'd say, because lambda is V over F, you've got delta X is V over F times L over 2D. Now, all of that bit, V, L, and 2D is a constant. So delta X varies as 1 over F, because that isn't changing. So as the frequency gets bigger, higher, as the frequency gets higher, this becomes a bigger number, then this must become smaller. So you would see that effect with a higher frequency. Okay, the fringe spacing becomes smaller. Okay, so that's the third consideration there. The last one is, well, what happens? Let's go back to Newton's rings. Okay, looking down from above, we've done this before. Looking down from above, you see that the fringes are concentric. They're circles. They're not bars. You see bars when you've got this arrangement, and you see this when you're looking down through your microscope, you'll see this. Now with the lens, you'll see these concentric circles. So looking down from above, you'll see concentric circles that look something like this. How the circles that are closest to the center are much thicker. Okay, in the same way that I talked before about how thick are the lines, okay, here we get the same thing, that the circles are much thicker in the center. Okay, right, now the other thing that happens, so we've got these circles, and as you get further and further out, the circles become thinner. Now this wedge is not a linear progression. This is a straight line progression. This is a curve, okay? And this curve, the air wedge, as you move out that way, the air wedge gets progressively bigger. It's not a linear relationship. as you go along here. You go along here a bit, you go up a bit, you go along twice as far, you go up twice as far, you go along 3 times as far, you go up 3 times as far. Here, it's not a linear relationship. You go along a little bit, you go up a little bit, you go along and double the distance that way, and you go much bigger separation between the 2 bits of glass. So you double the distance there, and perhaps this goes up by 3 times as much. You go up by 3 times the distance here, and perhaps this distance here goes up by 6 times as much. It's not a nice linear, steady relationship. So not only do the rings change their thickness, they're thicker in the center, the spacing actually changes, and as you get further away, the spacing becomes, let's get this right. I've really got to think hard about this. In fact, I drew this earlier and I've lost it, lost the plot completely here. The spacing changes. So here, let me go back a stage and gather my thoughts and have a look at the difference between that one and that one. The spaces here become thinner and closer together, thinner and closer together. So here the lines become thinner and closer together as we move out. So let's have the next one, which is about that sort of thick. Okay. And as we get further apart, this next ring is going to get closer and thinner. I think that's right. I might just have talked myself completely the wrong way around there. Thomas is probably sitting there cringing at what I've got to say. So there's 2 things going on. One is, how thick are the rings in terms of thickness that way, and how far apart are they separated? But I'm pretty sure that that's right. They become thinner and further apart. So what would happen if you didn't have this? What would happen if you just had 2 curved pieces of glass, 2 microscope slides? When you look down from above, you're going to see a microscope slide with another microscope slide stuck on top of it and something propping them up, and you'll see the fringes through the 2 pieces of glass like this, for instance. What would you see if you had a curved flat piece of glass and a straight piece of glass? And I think if I've got this right, you'll see a wide destructive interference fringe here, and as we go further away, the fringes become closer together and thinner. So the next one would be about there. It's thinner left to right, but closer there, and then we get to that sort of thing, and then we get to much closer still, and by the time you get right out to the end, you're going to have something that's pretty close and much thinner. I can't really do that. I want to get rid of a little bit of that just to finish it off there. So you're going to see 2 effects there, and that brings together some of the earlier stuff that I did. Now, I'm not going to do the maths of how thick the destructive interference fringe is, but you can certainly do the maths of what's the spacing, because we know that delta x is lambda L over 2D. So as D gets bigger on the bottom, delta x gets smaller, so that distance gets smaller. And you're just going to have to learn that the fringes are thicker when you've got a small distance and much thinner and closer together, much thinner that way and much closer together when you've got a bigger distance. And you can see that this is quite a bit of extra thought that goes into this, but that should give you an idea of what's going on there. I think I got all that right. It's just a bit of lateral thinking there to work out what 2 effects are you going to see all at the same time. And that's that. You should be able to do all of the Campbell-Robertson questions I'm going to ask you to do, and you should be able to do all of the exam questions. There aren't a lot of exam questions. CFE, Advanced Higher, which is what you're doing, has only been on the go for the last 4 years, I think. And if you go to past papers, you'll only find 3 questions. Has been one question on an aspect of this over the last 3 years, but the first year there wasn't one. So if you want to see some of these more variable questions, you're actually going to have to go back to see old advanced higher questions. Now, what do I mean by old advanced higher questions? You're currently doing CFE advanced higher, of which there are 4 papers, which is 2019, 18, 17, and 16. There's only 4 papers. But what happened in the year previous to that? So we've got 2019, 18, 17, 16. Obviously, 2020 wasn't used because nobody sat an advanced high paper last year. So 2020 isn't around, even though this is now 2021. And there won't be a 2021 paper either. But what happened in 2015? Well, in 2015, there was a previous edition of Advanced Higher. It was still called Advanced Higher, but it was called Revised Advanced Higher. And that was for 2 or 3 years before that. And that went back to about 2013. So there was probably 3 or 4 papers. I can't remember how many. What happened previous to that? There was something called Traditional Advanced Higher, which was on the go for many years, probably 10 years or something. Previous to that, it wasn't called Advanced Higher. It was called Certificate of 6th Year Studies. But there were still exams, and basically the physics doesn't change. It's just the SQA every couple of years decides to introduce a new system of exams, but the physics is roughly the same. Now, if you go onto the SQA website, you will only find those on the SQA website. If you want to see any question papers before 2016, they're not on the SQA website. And you will get some of these, not all of them, but you'll get some of these on a website that's hosted by a man called Mr. Mackenzie. And I've probably mentioned this before. Mr. Mackenzie, that's not Donnie Mackenzie. This is a different Mr. Mackenzie altogether. He's a physics teacher in Thurso, and he has a website which he calls Physics, spelt wrong because nobody up in Thurso knows how to spell physics properly. If you Google physics, Mr. Mackenzie, you'll get to his website. And on his website, you'll find all the previous papers that go back for years and years and years that you could have a look at. And remember, the physics doesn't change. However, they do put extra topics in and take stuff out. So be careful if you're looking at some of these. But I am going to provide you with some particular questions that I want you to do that go back. You will find these questions on the Mr. Mackenzie Physics website. You'll have to look that up. So one question, for instance, I think I'm wanting you to do, if I can find it, is from 2013, and you only go back to 2016 on the SQA website. So if I say, right, I want you to do 2013, and I think there's a question, which is question 8 from 2013. You go to Mr. Mackenzie Physics website, you'll find the 2013 paper. You'll be able to download the paper, the question paper itself, and you will also be able to download the solutions as a separate file from 2013. And you just have to have a look and say, right, I've downloaded the question paper, I'll have a go at the question, and then you can check yourself that you've got the solution correct by getting the equivalent 2013. And I think another one I wanted you to look at is question 10 in 2014, and you'll be able to do exactly the same. Is go and download the whole of the paper from 2014, have a go at question 10 and have a look at its solution from 2014 as well, and check that you've done it. Okay, I'm also going to ask you to do some Campbell-Robertson questions, and the Campbell-Robertson questions I want you to do are questions 91 up to 100. So I'm going to put that information in as your assignment. There's one extra question you can do. Out of these 4 papers, there's only one question which we can do at the moment, which is 2018. So question number 11 from 2018. And you'll see that 2018 is a CFE paper, and therefore it's on the SQA website. So you will be able to download, and it's a good idea to have these all downloaded as far as possible. Definitely the CFE papers. I'm not suggesting you download too many of these. Definitely do the 2013 and 2014, but get hold of the 16, 17, 18 and 2019 SQA papers. And what I want you to do is question 11 on the 2018 paper, and on the SQA website you will be able to get the paper and you'll be able to get the solutions, and you'll know no doubt how to download each of those. So there will be these Campbell-Robertson questions, which I suggest you do first, and then these questions that I want you to have a go at for exam questions afterwards. I will write that down as well in your assignment so you know what you're doing. Okay, but you could always stop the recording and write it down yourself. Those are the questions I want you to do in addition to the notes that I want you to get into line paper or wherever it is in your folder, wherever it is you're keeping all of this stuff, all the notes from the 4 lessons now. And then I don't want you to submit any of those notes. I just want you to submit these questions, photograph those, put them into a Google Doc, please, if you can manage that. If it's an image, it will go into a Google Doc. If it's a PDF, I don't think PDFs go very well into a Google Doc. So either upload separate PDFs or put all your images, if it's a JPEG or whatever format your camera does, PNG or whatever, put that into a Google Doc as you've done before with all of these questions and submit that. And I would like you to have all that done by next Monday, please. Next Monday, if today's the 8th, next Monday must obviously be the 15th, which would be our next lesson would be on Monday. So please get everything handed in before the lesson next Monday. Thank you.